Chapter 5, the definite integral, 5.2, definite integrals. Your objectives for this lesson are to express the area under a curve using limits and to evaluate a definite integral. Let's take a look. Okay, so starting off with sigma notation. If you were in pre-cal with me, you definitely saw this. You may have seen this in another math class though also. So this big zigzag here, looks like an E, is the Greek letter sigma. Sigma means sum. What you are summing is this function. So a sub k is our function. You're evaluating it starting at this bottom value here and stopping at the top value up here, the n. This would be expanded form, but as you can see, it is quite long. So that's really the reason why we use sigma notation, is because it allows us to express a large sum in a compact form. Today in class we looked at Riemann sums. You can express these using sigma notation also. So S sub n is our sum, and you can see we're going from k equals 1 up to n. This f of c sub k is our function. The only thing different from the last slide is this last bit, so delta x sub k. And this is, remember, delta means change, so this is our sub interval. So remember today, if we're looking at our graph, maybe this is the curve that we're looking at, really it's a straight line. So if I partitioned this, if this was 8 and this is 0, and I partitioned this into 4 equal pieces, then my subinterval is each one of these, which is 2. Okay, so it's like the width of my rectangle that I'm looking at. The longest subinterval length is called the norm of the partition, and is denoted by this symbol here. So again, what we looked at in class today and what I just showed you on the previous page, all of the subintervals are the same length, but sometimes that will not be the case. So if you had a function that was partitioned and you had one interval equals 2, one is 3, and one is 4, then the norm is 4 because that's the longest subinterval. Okay, you can write a definite integral. So remember, integrals are how you find the area under the curve. You can express the definite integral as a limit of Riemann sums. This says, let f be a function defined on a closed interval a comma b. For any partition P of a comma b, let the numbers c sub k be chosen arbitrarily in the subintervals x sub k minus 1, comma x sub k. If there exists a number I such that, you can see we have the limit as the norm approaches 0, and of the sum from k equals 1 up to n of the function f of c sub k times delta x sub k equals I. So this is I up here. That's I down there. Okay. No matter how p and the c sub k's are chosen, then f is integrable on a comma b, and I is the definite integral of f over a comma b. So that's a lot of words. Basically what this means is if I have a curve here, oh, let's fix that. Maybe this is my curve, and I want to find this area. I know that I can partition it into different rectangles and find my Riemann sum. So if I just did 2 rectangles and I did, maybe I'll do like a midpoint sum here. So I might get like this. Okay. But as you can see, I have a lot of area that should not be included, like here, that I'm including in my calculation, and then a lot of area that I'm not including right here. So the rectangular shape has a lot of errors with it. But if I wanted it to be more accurate, I could make these rectangles smaller. So again, still doing midpoint. Some smaller rectangles. And you can see, especially since I still have this one up here, the spaces with the smaller rectangles of the curve that are either left out or included when they shouldn't be are getting a lot smaller. And as it turns out, the smaller I make these rectangles, so as their width approaches 0, that's what this is really saying, the width of the rectangle approaches 0, then I'm going to have a perfect estimation, and all I'm going to be left with is what really is under the curve. Okay, so as the width of the rectangles for my Riemann sum approaches 0, I get the real value of the integral. The existence of definite integrals. This is a theorem. It says, all continuous functions are integrable. That is, if a function f is continuous on an interval a comma b, then its definite integral over a comma b exists. And I spelled integral wrong here, so sorry. It's definite integral. There we go. Which, sorry, just a second. This means that if you have a continuous function, then you can find the area between that function and the x-axis. Okay. The definite integral of a continuous function, a comma b. Let f be continuous on a comma b, and let a comma b be partitioned into n subintervals of equal length, where delta x equals, and delta x is the length of the subinterval. So subinterval length is delta x, which is equal to b minus a divided by n. It's like what we did today. So the stop point minus the start point divided by the number of partitions. Then the definite integral of f over a comma b is given by the limit as n approaches infinity of the sum from k equals 1 to n of f of c sub k times delta x, where each c sub k is chosen arbitrarily in the kth subinterval. So basically, if you had an infinite number of partitions, so instead of like 2 or 4, you have infinity partitions, that's when your width of each one will be 0. So as the limit, the limit as n approaches infinity for your Riemann sum, that will give you your definite integral. Okay, this is integral notation. So this big S here is called the integral sign. You do need to be able to label this for me for a quiz. So this is the integral sign. The a down here is the lower limit of integration. So b, you may have guessed, is the upper limit of integration. The function f of x is called the integrand, so integrand. And dx is the variable of integration. Okay. This is also called a dummy variable because when you integrate, it will go away. It will disappear. You don't really need it. I mean, you need to write it here, but when you're integrating, you're not going to use it. So this whole thing is the integral from a to b. Example 1. The interval -1, 3 is partitioned into n subintervals of equal length. Delta x equals 4 divided by n. Let m sub k denote the midpoint of the kth subinterval. Express the limit, so the limit as n approaches infinity, of the sum from k equals 1 to n of 3 times m sub k squared minus 2m sub k plus 5 times delta x as an integral. Okay, so the first thing that I need to point out here is that although m sub k, so these things here, represent the midpoint of whatever term we're at in the interval, they didn't have to be midpoints. So these points did not have to be midpoints for this problem to work. They could have been chosen from subintervals in any arbitrary fashion. So I could have said that they're the, I don't know, 3/4 of the way across the subinterval, and it would still work the same way. So we're going to rewrite this limit as an integral. So I'm going to draw my integral, so my integral sign here. I see my interval is from -1 to 3, so -1 to 3 of my function is 3x squared. So I'm replacing that midpoint with an x because it could have been any point on the interval, minus 2x plus 5 dx. You need to write the dx there. And this is our answer. Definition of area under a curve. So as a definite integral, and I've mentioned this a couple times now, so it's good that we're talking about it. If y equals f of x is non-negative and integrable over a closed interval, a comma b, then the area under the curve y equals f of x from a to b is the integral of f from a to b. Okay, so the important parts here, your function has to be non-negative. So I don't have, this does not apply at this moment to function like this. So if this is at x equals 10, I could not integrate, I could not find the area under this curve from 0 to 10 because this part is negative. So this is only working for the positive stuff. Deal with negative in a little bit. Example 2, evaluate the integral. So from -2 to 2, integrating square root of 4 minus x squared dx. So this graph, if we were to graph it, and you could use your calculator to do that, is actually a semicircle. Let's see how good of a job I can do drawing a semicircle. Not terrible. So it is a semicircle, and it goes from -2 to 2. If you wanted to figure that out with pencil and paper, you could just set this equal to 0 and solve that. So, like that. So it is non-negative on this interval, so we can use the definition that you just saw. So we're actually going to use some geometry to solve this, though. So since it's a semicircle, even though it's a little flat looking, I know that the area of a circle is pi r squared. So the area of a semicircle is going to be 1/2 pi r squared. Remember, semi means half. So my radius is halfway across the circle, so 0 to 2 means my radius is 2. So my radius, I'm going to plug in here, so 1/2 pi times 2 squared is 1/2 pi times 4, which gives me 2 pi. So the area under this curve, I could shade this all in, and oh, I can use my highlighter. So I could shade all this in. This is the area. And it is 2 pi. Alright, now let's look at what happens when your y value is negative. So going back to this image, what I shaded in blue. When y is negative, so f of x is less than 0, your area is also negative. So that's what this means here. And this is important for you to know. Basically, when you're integrating, you're going to subtract, so area above the x-axis minus area below the x-axis. So again, going back to this picture here, if I found that under this curve is 10, and in this curve I have 3, my area would be 10 minus 3, which is 7. So this is important. Please, please, please remember this. The integral of a constant. If f of x equals 0, where, not 0, sorry, c. If f of x equals c, where c is a constant on the interval a, b, then when you integrate from a to b, f of x dx, you're really integrating c, and you get c times b minus a. Example 3. A train moves along a track at a steady meaning constant, 75 miles per hour from 7 a.m. to 9 a.m. It's a long trip. Express its total distance traveled as an integral. Okay, and just to draw a picture for you, I like pictures. So 75 miles an hour, that's like up here. Okay, so this is our y equals 75, constant function. And we're moving from 7 a.m. to 9 a.m. No, it's only 2 hours actually. So this is 7 and this is 9. If we wanted to find the area, we would just say 7 minus 9 is 2 times 75, and this is 150. Okay, so 2 hours, 75 miles per hour gives us 150 miles. But let's do this without this picture in rectangle. So using the property that we just saw. So we're integrating from 7 to 9, this function, 75, and we're talking about time, so dt. This equals our constant function times upper limit minus lower limit. So this is 75 times 2, which is 150. So this way is a little bit shorter just because you don't have to draw a picture. And don't forget your units there. We know we're traveling miles, so 150 miles, 2 hours. Not too shabby. Okay, example 4, evaluate numerically. And this is a very exciting moment for you because we're going to evaluate these derivatives using the calculator. So what you're going to do, turn on your calculator and hit the math button and go down to number 9. So it should say FNINT and hit enter. You're going to enter in the function that's written here. So in this case we have x sine x. Close the parentheses on sine, but not on the FNINT, comma, x, comma, the lower bound is -1, so -1, comma, the upper bound, which is 2. Close your parentheses and hit enter. And you should have about 2.043. That's what we're going to write here. So it's approximately 2.043. Okay, we're going to do this again. This is our function, but be careful with the parentheses. Just watch how I enter it in for you. So again, going to go to math, number 9, and our function is 4 divided by parentheses 1 plus x squared, close parentheses, comma, x, comma, lower bound, which is 0, comma, upper bound, which is 1. And putting that in, we get about 3.142. So rounding to 3 decimal places, 3.142. Okay, part C. Again, we have to be careful with our parentheses here. So math, number 9, and our function is e to the, and it opened parentheses for us, which is nice, negative x squared, close parentheses, comma, x, comma, 0, comma, 5, close parentheses, and we get 0.886. Okay, so 0.886. And that is how you evaluate derivatives in the calculator. Okay, moving on. We want to, sorry, I said derivatives, I meant integrals a second ago. We are going to integrate from -1 to 2 the function absolute value of x divided by x dx. And if you remember from earlier in this course, the absolute value function is often broken into a piecewise function. So if I evaluated absolute value of x over x when x is greater than 0. So if I put in a 2, I would get 1. But if I did this for x is less than 0, so if I put in like a -7, I'd have 7 divided by -7, which will give me a -1. Okay? So really, what we're integrating here is a piecewise function. So for values greater than 0, my y value is 1, and down here it's a -1. And we're going from -1 to 2. Okay, so this is 2, this is -1, 1, -1. And I'm going to do this using area of rectangles because that's very easy. So this length is 2, and this width is 1. 1 times 2 is 2. From -1 to 0, I have 1 unit, and here I have 1 unit, so this is 1. But since this is below the x-axis, really it's a -1. So 2 minus 1 gives me an area of 1 unit. Okay, so that is example 5, and really that's the end of this lesson.